Before we begin, find yourself somewhere comfortable. Let your body settle, your breathing slow. This is a story told at the pace of starlight, meant for those quiet hours when the mind is ready to wander and wonder. There is nothing here you need to remember, nothing you need to solve. It is perfectly fine to simply listen. And if sleep arrives along the way, the universe will not mind at all. Somewhere in the dark between galaxies, far beyond the reach of familiar constellations, two invisible points of mass can spend 1 billion years moving in gentle circles. From a distance, nothing seems to change. No warning light flickers on, no glow grows brighter. Space looks as it always has, calm and indifferent, as if nothing important is happening at all. And yet, in those slow, patient orbits, a quiet story is being written, one that will someday release more energy than entire galaxies can shine at once. When that moment finally arrives, it comes faster than a human heartbeat. The universe opens a hidden door and lets an impossible amount of light spill through. For a brief time, the sky carries a glow that should not exist, bright enough to rival billions of stars combined, and then, just as quickly, it fades. Days later, sometimes hours, the light is gone again, leaving almost no trace that it was ever there. These events are called kilonovae, though the name can be misleading. It suggests spectacle, fireworks, something meant to be seen. In reality, they are among the rarest and quietest events the universe produces, not because they lack power, but because they are so easy to miss. They happen far away, fade quickly, and offer no advance notice. The universe does not pause to make sure we are watching. Only a handful have ever been confirmed. Not because they are unusual in cosmic terms, but because our eyes and instruments are small and the sky's very large. Space is full of explosions, yet most of them unfold without witnesses. A kilonova reminds us that brightness does not guarantee attention, and that some of the most important moments in reality pass unnoticed, simply because no one was looking in the right direction at the right time. If something can be that powerful and still remain almost invisible, it invites a gentler question rather than an urgent one. How much of the universe is happening without us? How much beauty, how much violence, how much creation unfolds in silence, with no audience at all? It is not a failure of observation, it is simply the scale of things. A kilonova begins when two extreme objects meet. Sometimes it is two neutron stars colliding. Sometimes a neutron star meets a black hole instead. In either case, gravity is pushed to its absolute limit. In a matter of seconds, the energy released can exceed what a star like our Sun will produce across its entire 10 billion year lifetime. It is the difference between a candle burning patiently on a table and a single bolt of lightning emptying the sky in one blinding instant. But even that comparison falls short because a kilonova does not only produce light, it also sends out ripples through space itself. The collision shakes space-time, launching gravitational waves outward in every direction. These waves carry information before any glow appears, as if the universe speaks in a low, quiet language first, and only later allows itself to be seen. Inside the debris thrown outward by this collision, something even stranger occurs. Under conditions so extreme they cannot be recreated on Earth, atoms begin to capture neutrons faster than they can fall apart. Elements heavier than iron are built in moments: gold, platinum, uranium. Materials that feel solid and permanent in our hands are born from an event so brief it barely exists in time at all. Destruction becomes a kind of factory, and violence turns into inheritance. It can feel unsettling to realize that objects we associate with beauty or stability trace their ancestry to catastrophe. Yet the universe has never separated creation from collapse. It breaks things apart in order to build something new, and it does so without drama, without intention, without apology. This is not cruelty. It is simply how matter changes form. If kilonovae are responsible for shaping so much of what makes planets complex and interesting, then another question naturally rises, quiet but persistent. What kind of object can survive long enough to create such an ending? What sort of star can pack the mass of a sun into a sphere no wider than a small city and still resist collapsing into nothing at all? At the heart of every kilonova story is an object that feels almost like a contradiction, a star that is already dead, yet heavier than the sun. A body only a few dozen kilometers across, yet dense enough to bend space so severely that even light struggles to escape its surface. These objects exist on a knife's edge, balanced between being something and becoming a black hole. They are called neutron stars, and they are not loud or flashy on their own. Most of the time they sit in darkness, spinning quietly, holding themselves together through a fragile truce between gravity and the fundamental forces of matter. They're reminders that survival does not always look peaceful, and that stability can be an ongoing effort rather than a permanent state. In the next part of this story, we will slow down and move closer to these strange remnants. We will explore how they form, how they endure, and why their very existence tells us something profound about the limits of matter itself. There is no rush. Neutron stars have been waiting for billions of years already, and they can wait a little longer while you rest. When we left the story, we were standing at the edge of something barely holding together. A star that has already died, yet refuses to disappear. A remnant so small it could fit inside a city, yet so heavy it bends the space around it like stone pressing into soft ground. To understand how a kilonova becomes possible at all, we have to sit quietly with these objects for a while. Not rushing past them, not demanding answers too quickly, but allowing their strangeness to unfold at its own pace. A neutron star begins its life as something familiar. Long before it becomes dense and silent, it is simply a massive star, bright and burning, fusing light elements into heavier ones deep in its core. For millions of years, that fusion creates a steady outward pressure, a kind of internal breath that holds gravity at bay. The star exists in balance, not because gravity is weak, but because something is pushing back just hard enough. Eventually that balance fails. Fuel runs out. The outward pressure fades. Gravity, patient and relentless, finally wins. The core collapses inward, faster and faster, until matter itself is forced into a new state. Protons and electrons are pressed together so tightly they merge, becoming neutrons. What remains is not ash or dust, but a compact kernel of almost unimaginable density. A neutron star is born not from explosion alone, but from surrender. It helps to picture the entire mass of our Sun compressed into a sphere only a few tens of kilometers wide. Not spread gently, but packed so tightly that empty space between particles nearly disappears. A single teaspoon of this matter would weigh billions of tons. Mountains would collapse under it. Planets would fracture. And yet, somehow, it holds together. Ordinary atoms cannot survive conditions like this. Chemistry ends here. The familiar rules that govern solids, liquids, and gases no longer apply. Inside a neutron star, matter is pushed beyond the realm of everyday experience and into nuclear physics. The star becomes something like a single giant atomic nucleus, scaled up to the size of a city, each neutron pressed against the next with nowhere left to go. This is why neutron stars live on a narrow boundary. Add too much mass and gravity overwhelms even this extreme state, pulling everything inward until a black hole forms. Remove just a little mass, and the star might not exist at all. Their survival is not guaranteed. It is negotiated moment by moment, held together by forces that feel abstract until you remember that they are shaping something real. Gravity at the surface of a neutron star is overwhelming, hundreds of billions of times stronger than what we feel on Earth. Standing there, if standing were possible, would not feel like standing on solid ground. It would feel like leaning into a deep well where every step pulls harder than the last. Space itself curves sharply, and time slows, stretched thin by the star's weight. These are not poetic descriptions. They are the geometry of reality under strain, and gravity is only part of the story. Many neutron stars carry magnetic fields trillions of times stronger than Earth's. Fields so intense they can twist charged particles and radiation into rigid paths, shaping the space around them into invisible structures. Some of these stars spin hundreds of times per second, sweeping beams of radiation across the cosmos like slow, steady lighthouses. From Earth, we see those beams as pulses, arriving with such regularity that they rival atomic clocks. These pulses are not showing off. They are simply rotating, carrying the memory of a violent birth forward in time. Their steady rhythm tells us that despite their chaos of origin, neutron stars can be astonishingly stable. They hold their spin, they keep their pace, they endure. Yet beneath that apparent calm, uncertainty remains. We cannot see inside a neutron star. No telescope can peer through that density. The outer layers are understood in broad strokes, but deeper down, matter may take on forms we have never observed. Neutrons may dissolve into more fundamental particles. The core may behave like an unfamiliar fluid, dense and strange, obeying rules that exist only under such pressure. Neutron stars are laboratories the universe built for itself, places where physics is tested far beyond what human machines can recreate. By measuring how massive they are, how wide they stretch, how they spin, and how they deform under gravity, we gather clues about what must be happening inside, not by opening them, but by listening to how they respond. This quiet listening matters, because neutron stars are not isolated curiosities. They move through darkness. They orbit companions. Sometimes they find each other. When two of these objects share a system, gravity binds them together, not gently, but with long-term commitment. Their existence becomes intertwined, their futures aligned. At first, nothing about this partnership feels urgent. Two neutron stars can circle one another for millions or even billions of years, locked in a slow, steady dance. From far away they look permanent, almost timeless. Yet this is the illusion gravity often creates. What feels stable is sometimes only slow. In the next part of the story, we will follow that dance. We will watch how patience turns into inevitability, how energy is quietly drained away, and how an orbit that seems eternal becomes a path with only one possible ending. There is no need to hurry there. The spiral inward is gradual, and the darkness between steps is wide enough to rest in. For a long time, nothing seems to change. Two neutron stars can share the same stretch of darkness for ages, bound together by gravity in a way that feels almost gentle. They circle one another like heavy stones tied to an invisible rope, moving through space with a rhythm so slow it suggests permanence. From far away there is no sense of danger, no signal that anything dramatic lies ahead. The universe appears patient, and patience has a way of feeling like safety. These pairs do not begin as neutron stars. Long before they become dense and quiet, they start as two massive suns born together in the same stellar nursery. They grow side by side, burn their fuel side by side, and age within the same neighbourhood of space. When the first one dies, it does so violently, erupting as a supernova that should, by all rights, tear the partnership apart. Often it does. But sometimes, gravity holds on. The system survives the blast as if the universe has decided the story is not finished yet. Then, much later, the second star dies too. Another explosion, another test of balance, and sometimes, against expectation, the bond remains. What is left behind are two neutron stars locked together, both remnants of earlier endings, now sharing a future shaped entirely by gravity. They do not rush toward it, they orbit. Days pass, years pass. Civilizations could rise and fall beneath their steady motion without ever knowing they were there. In some systems, the orbit continues for billions of years, longer than complex life has existed on Earth. This is what makes the eventual outcome so unsettling. The countdown is slow enough to feel like forever, but every orbit has a cost. As the two neutron stars swing around each other, they disturb the fabric of spacetime itself. Their immense mass drags at the geometry of the universe, sending ripples outward, like waves spreading across the surface of deep water. These gravitational waves are not light. They do not glow or flash. They carry energy away silently, draining the system a little at a time. The loss is subtle. With each orbit, a tiny amount of energy leaks into the universe and never returns. The change is so small it would be impossible to notice without listening very carefully. Yet it is relentless. The orbit shrinks. The stars draw closer. What looks like a stable dance is in truth a slow surrender. For a long while, the difference is almost nothing. Watching it would feel like watching stone erode, or a glacier inch forward across a valley. The universe seems unhurried, unbothered by the passage of time. This slowness can be comforting. It invites the illusion that nothing urgent is happening, that there is always more time. But patience is not the same as mercy. The energy lost to gravitational waves cannot be recovered. There is no mechanism to push the stars back apart. The spiral inward is inevitable, even if it takes longer than memory itself. The orbit tightens quietly, faithfully, one revolution at a time. As the distance between the stars decreases, something subtle begins to change. The pace increases. What was once a stately motion becomes quicker, then quicker still. Millions of years pass, and the system hardly notices. Then thousands, then centuries. The approach accelerates, not because anything new has happened, but because gravity is finally being allowed to show its full strength. In the final stages, the two neutron stars whirl around each other at a significant fraction of the speed of light. They can complete dozens of orbits every second, city-sized spheres heavier than the sun spinning so fast that space between them becomes turbulent. Spacetime itself begins to distort violently, not as a metaphor but as geometry under stress. Distances stretch and compress. Time behaves strangely. Straight lines bend. This is not chaos. It is precision taken to an extreme. For millions of years, the system whispers. Gravitational waves leak away softly, carrying information no one hears. Then, slowly at first and then all at once, the whisper grows louder. The frequency of the waves rises, their strength increases. The universe begins to speak more clearly, as if leaning closer. By this point, there is no decision left to make. The stars are no longer simply orbiting. They are falling toward each other, locked into a final approach that cannot be stopped. Gravity is no longer a background influence. It has become a direct force shaping every moment. From the outside, there is still no flash, no warning flare. The darkness holds. This is one of the strangest aspects of the story. The most violent moments are preceded by the quietest ones. The universe does not announce what it's about to do. It just continues. In these last seconds, the separation between the stars collapses rapidly. The space that once felt wide enough to be safe vanishes. Their immense gravity reaches across the gap, pulling at crusts, distorting shapes, stretching matter toward its breaking point. The objects that once seemed whole begin to feel strain. And still, until the very end, it is quiet. This long, slow descent is what gives the collision its weight. It is not a sudden accident. It is the end of a commitment that began long before any observer could have known it existed. Two stars born together, died separately, and spent eons circling in darkness, losing energy grain by grain until only one outcome remained. In the next moments of the story, patience finally runs out. Gravity stops being subtle and becomes destructive. Crusts will crack. Fields will tangle. Matter will be torn loose and thrown outward. The silence will break. But for now, it is enough to sit with the spiral itself. To recognize that endings in the universe are often prepared far in advance, shaped by forces so steady and so quiet that they feel almost kind. If you feel yourself drifting here, that is perfectly fine. The stars have been drifting too for a very long time, and they will wait just a little longer before everything changes. In the final seconds of their long descent, gravity stops behaving like a distant influence and becomes something immediate, something physical. What was once a slow tightening now turns into a direct pull, as if the universe has finally gathered all its patience and decided to let go of restraint. The two neutron stars are no longer simply moving toward each other. They are being reshaped by the force that binds them. For most of their shared history, each star was whole. Dense, yes. Extreme beyond intuition, but intact. Now that wholeness begins to fail. The gravity of one star reaches into the body of the other, tugging at its surface, stretching it slightly out of shape. The effect is subtle at first, like a distant tide lifting water almost imperceptibly. Then the pull strengthens and the distortion deepens. Neutron stars have crusts, rigid outer layers formed from tightly packed nuclei, arranged in a lattice as solid as anything nature allows. These crusts have endured unimaginable pressure for millions of years, but now, under the strain of another star's gravity, even this structure begins to crack. The surface fractures not with sound, but with release, like ice breaking on a frozen lake that has carried too much weight for too long. Those fractures matter, not because they are dramatic, but because they mark the moment the stars stop being sealed objects. They begin to leak. Matter loosens its grip and becomes mobile. no longer confined to the surface it once called home. The boundary between star and space starts to blur. At the same time, something invisible but powerful is happening around them. Each neutron star carries an enormous magnetic field, lines of force extending far into the surrounding darkness. As the stars spiral closer, those fields collide. They do not merge smoothly. They twist, knot, and snap, reconnecting in sudden releases of energy. Invisible springs wound tighter and tighter finally give way. This magnetic chaos feeds the violence of the moment, shaping how energy flows and where matter is thrown. Gravity may be the architect of the collision, but electromagnetism becomes an active participant, stirring plasma, accelerating particles, and helping to drive material outward. The final moments are not governed by a single force, but by a conversation between them. Then the real ejection begins. As the stars plunge together, tidal forces tear matter from their surfaces and fling it outward at incredible speeds. This is not a gentle shedding. It is a spray, a storm of neutron-rich debris hurled into space, carrying the raw ingredients for transformation. The speeds involved are so high that ordinary comparisons fail. Time and distance lose their familiar meaning, stretched thin by motion and gravity. This escaping material is crucial. Without it, there would be no visible aftermath, no glow to chase across the sky, no chemical legacy. How much matter escapes, and in which directions, determines what the universe will later reveal to distant observers. Some of it forms a broad cloud, some of it is funneled into narrower streams, none of it remains untouched. As matter flies outward, space-time itself responds. The gravitational waves that have been whispering for millions of years suddenly rise in pitch and strength, climbing toward a final note. This is the chirp, a brief surge marking the last stable orbit in the moment of impact. It lasts only milliseconds, yet it carries a detailed record of the collision, encoded in the shape of the wave itself. The merger happens faster than thought. In less time than it takes to blink, two objects heavier than the Sun collide, distort, and become something new. The energy released in those moments rivals the combined light of entire galaxies. Matter and energy blur together under conditions that exist nowhere else, and then begin to separate again, flung outward into the dark. From this chaos, something focused can emerge. A jet may form, a narrow beam of radiation powered by the newborn remnant and the disk of debris swirling around it. This jet moves near the speed of light, drilling through the surrounding matter like a cosmic needle. If it happens to point toward Earth, it appears as a brief gamma-ray burst, intense and fleeting. It is tempting to imagine this jet as a beacon, announcing the event to the universe. In reality, it is selective. Only a small fraction of observers ever see it directly. Most kilonovae likely go unseen simply because their beams are not aimed our way. The universe does not guarantee visibility. It only guarantees that the event happened. What makes this moment unique is not just the violence, but the messengers it sends. Gravitational waves race outward, carrying information about mass and motion, about the final dance and its end. Light follows, slower, layered, unfolding over time. The universe speaks in more than one language at once. By the time any glow becomes visible, the space-time ripples have already passed through distant worlds, stretching and squeezing space by amounts so small they almost seem imaginary. Yet they are real. They are the first announcement delivered quietly before any photon arrives. This is where the collision stops being only an ending and becomes a beginning for understanding. When gravity and light carry the same story in different forms, they allow a deeper listening. They turn a fleeting event into something that can be reconstructed, not perfectly, but meaningfully. Still, even here, there is no need for urgency. The most intense moments are already over. What remains is aftermath, expansion, cooling, and change. The universe exhales, letting debris drift outward like dust settling after a collapse. In the next part of the story, we will follow that debris as it cools and glows, as new elements take shape within it, and as the collision leaves behind something altered but enduring. There is no rush to get there. The light itself takes time to unfold, and it will continue long after the sound of the collision has faded. If you feel yourself drifting now, that is perfectly natural. Even after the most violent moments, the universe always returns to patience. After the collision has passed, after the brief violence has exhausted itself, the universe does not rush to explain what it has done. It settles instead. Debris continues to move outward, thinning and cooling, carrying with it the memory of forces strong enough to reshape matter itself. The light that follows is not a single flash, but a slow unfolding, layered and patient, as if the universe is taking its time to speak clearly. Within that expanding cloud, something remarkable is happening. The material torn from the neutron stars is rich with free neutrons, so dense that atomic nuclei are forced into rapid growth. Neutrons are captured faster than they can decay, building heavier and heavier elements in a matter of seconds. This is not the steady fusion that powers ordinary stars. It is a brief, overwhelming flood, more like a river breaking through a dam than a fire burning calmly. Gold is formed here, platinum, uranium. Elements that feel solid and enduring in our hands are assembled in a moment of frantic creation, then cast into space. The glow of the kilonova is powered by this process, by the radioactive decay of newly made atoms as they release energy and settle into more stable forms. The light rises, shifts in colour, and slowly fades as the debris expands and cools. It is easy to imagine this as an ending, a dramatic conclusion to a long story. But in truth, it is a beginning that stretches far beyond the moment itself. The elements forged in this collision do not disappear when the light dims. They continue outward, mixing with the gas between stars, seeding future clouds that will one day collapse into new suns and new worlds. This is how the universe practices patience. It breaks things apart quickly, then waits a very long time for the consequences to unfold. Every rocky planet carries this history quietly. The iron in its core, the gold in its crust, the uranium warming its interior are not local inventions. They are inheritances, passed down across billions of years from rare and distant catastrophes. Even the heat that drives tectonic plates and keeps worlds geologically alive traces its origin to processes like this, to atoms assembled in violence and delivered gently over time. As the debris cloud continues to expand, attention turns inward, toward what remains at the centre. 2 neutron stars have become one remnant, and nature has only a few ways to resolve the balance of mass and motion left behind. Sometimes the outcome is immediate, the combined weight is too great, and gravity collapses everything inward, forming a black hole almost at once. Space closes in on itself, and the story takes on a new shape defined by horizons and silence. In other cases, the universe hesitates. The remnant may briefly survive as a hypermassive neutron star, spinning so rapidly that rotation holds gravity back, like a stone kept aloft by motion alone. This state cannot last forever. Energy is lost, the spin slows. Eventually, gravity claims its victory. But for a short time, this unstable object can drive powerful winds and radiation, reshaping the debris around it and altering how the kilonova's light evolves. Whether the end state is a black hole or a delayed collapse, the impact does not vanish when the light fades. Spacetime itself has been altered. Energy has been carried away by gravitational waves. Matter has been redistributed. The surrounding region of the galaxy will never be quite the same, and still, the universe does not dwell on any single event. In an average galaxy, a kilonova may happen only once every 100,000 years. That sounds rare enough to feel distant, almost hypothetical. But the universe does not contain one galaxy. It contains trillions. Somewhere, even now, a pair of neutron stars is spiraling inward, already committed to its final orbit, already sending faint ripples through space-time. Whether those ripples will pass unnoticed or be caught by listening instruments is a matter of timing and chance. Detectors must be watching. Telescopes must turn quickly. Clouds must not be in the way. The difference between discovery and silence can be a single missed night. This has changed how humans observe the universe. Astronomy is no longer only about looking. It is also about listening, about coordinating senses, about waiting quietly for signals that arrive without warning. When gravitational waves are detected first, they narrow the search, guiding eyes to the right patch of sky before the light fades. Chance becomes collaboration. Each new observation adds detail. The masses become clearer, the geometry sharper, the story of element creation less abstract and more tangible. With every event, understanding deepens not through speed, but through accumulation, through patience rewarded over time. The universe still keeps many of its secrets. Neutron star interiors remain hidden. The exact paths of jets are not fully mapped. The total contribution of kilonovae to the elements of galaxies is still being refined. Mystery remains, not as a failure, but as an invitation. And so the story returns to where it began, not with spectacle, but with quiet reflection. If the atoms that make up worlds and bodies and quiet rooms at night were shaped by rare, distant collisions, then connection stretches farther than it first appears. We are linked to events that unfolded long before memory, carried across space by patience alone. Somewhere out there, gravity is tightening its grip once more. The universe is preparing another quiet explosion. Whether we hear it coming or not, the process will unfold as it always has, unhurried, precise, and indifferent to attention. If you find yourself drifting now, that is perfectly all right. The universe does not demand witnesses. It continues, carrying stone into darkness, darkness into light, and light back into rest, one slow transformation at a time. As the story settles, there is nothing left to follow, and nowhere left to go. The universe continues on its own, quietly, without needing our attention. Stars will keep forming and fading, gravity will keep shaping distant paths, and somewhere far away another slow spiral is already underway, moving at a pace so patient it does not mind being forgotten for a while. You do not need to hold on to any of this. The science can rest now, the questions can drift, and the answers can remain unfinished. Like the night sky itself, understanding does not demand focus. It simply exists, waiting gently whenever you feel like looking again. For now, let the darkness be kind. Let your thoughts loosen and fade the way distant light does, thinning until it blends back into silence. The universe has carried this story for billions of years. It will carry it still, whether you are listening or sleeping. Thank you for sharing this quiet stretch of time. Good night, and rest well.